It was powerful enough for tugboats, mining rigs, and offshore vessels. But one hidden weakness turned remote jobs into a deadly gamble. This is the story of how the Detroit Diesel 12 V71 rose to power, and how that power came at a cost few saw coming. When Detroit Diesel added the 12 V71 to the 71 series lineup in the 1950s, the country was growing fast. Hauling got heavier, work sites got rougher, and the machines that had handled the loads before were starting to show their limits. The 12 V71 was the answer for those heavier loads and tougher conditions. On land, you'd find it under the hoods of logging trucks driving down steep mountain roads, where the weight behind the rig made every mile a risk. Breakdowns weren't just expensive, they were dangerous. Drivers counted on this engine because it could take the strain. In the pits, mining crews needed equipment that kept working deep underground, where help wasn't easy to find. That's where the 12 V71 came in. It ran equipment that couldn't afford to quit. Out on the oil fields and along pipelines, it kept pumps going day and night, moving fuel and product where it needed to go without stopping. Nobody chose the 12 V71 because it was pleasant. It wasn't. It shook the cab, left oil stains, and made more noise than most could stand for long stretches. But it kept working. That was what mattered. It was dependable in places where that was the only thing keeping the job going. Out at sea, the engine built an even bigger reputation. In the marine industry, it showed up on tugboats that moved ships up narrow channels. Offshore supply boats trusted it to carry crews and equipment to rigs where failure wasn't an option. On fishing boats, it ran steadily on long trips through open waters. Marine crews liked it because it brought them back. Breaking down miles out at sea wasn't something anyone wanted to confront. It wasn't perfect, but it was simple. No electronics to fail, no complicated systems to fuss with. If something went wrong, you could usually fix it with the tools on hand and get back to work. The difference between land use and marine use came down to the price of failure. On land, a busted engine meant downtime, lost money, maybe a long recovery job. At sea, it could mean losing the boat or worse. That's why, despite the leaks, the noise, and the fuel burn, crews kept trusting it. And that's how the 12 V71 rose to power. It wasn't because it was the smoothest or the cleanest engine. It was because it kept equipment moving in places where nothing else lasted. At the heart of the 12 V71 was a two-stroke design that meant a power stroke with every crankshaft revolution. A hallmark of its efficient two-stroke setup that delivered more power strokes per revolution than a four-stroke engine. That gave it an edge in power-to-weight ratio and simplicity. Each of the 12 cylinders displaced 71 cubic inches, giving the engine a total of 852 cubic inches, or 14 liters. Air entered through ports in the cylinder liners rather than through intake valves. The Roots-type blower mounted on the side of the engine forced air into those ports, driving the scavenging process, clearing out exhaust gases and filling the cylinder with fresh air for combustion. The blower didn't produce high boost pressure like a turbo would, but it delivered exactly what was needed for the two-stroke cycle to function. That meant the engine stayed simple. Fewer moving parts, no complex valve train on the intake side, and less that could go wrong under hard use. The naturally aspirated models, more accurately described as blower-only versions, were common on land. They typically produced 350 to 390 horsepower at 2100 RPM and around 1000 to 1100 pound-feet of torque at 1200 RPM. This wasn't about peak horsepower, it was about torque and durability. Logging trucks, mining equipment, and oil field pumps needed steady pulling power and a block that could take years of punishment without falling apart. Marine operators favored the turbocharged versions for extra power where it mattered. In higher output configurations, marine turbo models could deliver 675 to 750 horsepower at 2100 RPM and 1500 to 1600 pound-feet of torque at 1200 RPM. Twin turbochargers fed air into the blower, allowing the engine to burn more fuel and produce more power without making the engine physically larger. That kept installations compact while delivering the muscle marine crews needed for demanding work at sea. One of the 12 V71's key features was its use of replaceable dry cylinder liners. Unlike wet liners that sit in direct contact with coolant, dry liners are surrounded by the engine block itself. This made them simpler to seal and less prone to coolant leaks, an advantage in tough environments where reliability came first. If a liner wore out, it could be replaced in the field without pulling the engine. But dry sleeves like these often required more effort to remove than wet liners. Mechanics typically use special tools and sometimes the piston's motion to press out the old liner. It took work, but it avoided a full engine teardown. The long piston skirts were another important design feature. On a two-stroke diesel, the pistons take a lot of side loading because of the large forces involved in the rapid power cycle. The long skirt helped distribute that load more evenly, reducing abnormal wear and keeping the piston stable inside the bore. That was critical in applications where engines ran under full load for hours or days at a time. The fuel system was as practical as the rest of the design. The 12 V71 used mechanical unit injectors. No electronics, no sensors, no fragile wiring to break or corrode. Each injector was driven by its own rocker arm, delivering fuel directly into the cylinder at high pressure. If an injector went bad, it could be swapped out quickly with basic hand tools, even in the field. Marine cooling systems were built for endurance. Keel cooling setups eliminated the need for seawater to circulate inside the engine, reducing corrosion risk. For those engines that did use raw water cooling, robust strainers helped prevent clogging from debris. The raw water inlets were designed for marine conditions, built to last, with serviceable connections and filters that could be cleaned easily. The oil system was oversized for durability. The typical oil capacity was around 13 gallons, depending on the pan configuration, with multiple points for filling and filtering. That gave operators extra margin in demanding jobs, reducing the risk of oil starvation on steep grades or in rough seas. The engine's reverse gear and transmission options gave marine operators flexibility. Various reduction ratios allowed boats to match engine output to propeller speed for different conditions, from tight harbor work requiring fine control to faster runs in open water. The transmissions were built to handle the torque of the engine without slipping or overheating under load. The 12 V71 earned its place because it delivered power, durability, and serviceability in the toughest jobs. But with that reputation came a trust so deep that few ever saw the risk hiding underneath. The 12 V71 was renowned for its toughness, yet many overlooked how critically that toughness relied on a single system: its air supply. Without it, all the engine's inherent strength was irrelevant. The engine's two-stroke cycle relied entirely on that steady, forced airflow. The Roots blower wasn't a performance upgrade or an optional piece of equipment. It was what kept the engine alive. With every turn of the crankshaft, the blower had to push fresh air through the cylinder ports, clearing out the exhaust and filling the space for the next combustion cycle. There was no backup plan. Without that airflow, combustion simply couldn't happen. On marine turbocharged versions, the air system's role was even more critical. The twin turbos didn't just add power for the sake of speed. They worked in tandem with the blower to deliver the volume of air the engine needed to keep up with the demands of marine work. The turbos helped keep the cylinders filled at the right pressure, making sure the scavenging process operated optimally. If either the blower or the turbos failed, the engine was done. What made this setup risky was how little margin there was for error. A four-stroke engine could often run badly, but run with an intake or exhaust restriction or even a partial failure. The 12 V71 couldn't. If the air supply faltered, it didn't slow down, it stopped. Failures in the air system could happen suddenly. A stripped blower drive gear, a seized rotor inside the blower housing, or a turbocharger that locked up mid-run, any of these could bring the engine to an instant halt, and these failures didn't give much warning. The blower gears and drive shafts lived under constant stress, and when something went, it often went all at once. Marine operators learned this the hard way. A tugboat working a narrow channel might lose power as the blower drive stripped, leaving the vessel at the mercy of current and wind with no time to react. Offshore supply boats, dependent on their engines for both propulsion and onboard systems, could find themselves dead in the water if a turbo or blower failed. And when the weather turned bad, or when rigs and hazards were nearby, that wasn't just inconvenient, it was dangerous. The same risk showed up on land. Logging trucks climbing steep grades with full load sometimes suffered catastrophic air system failures. The engine would stall without warning, leaving the driver scrambling to keep control as the heavy load pushed downhill. In mining operations where machines were far from immediate help, a failed blower could leave equipment stranded in places that were difficult or hazardous to recover. One of the most dangerous aspects of this design weakness was how easy it was to overlook the early signs. The 12 V71 was a noisy, vibrating, leaking engine at the best of times. A bit more vibration, a slight change in the exhaust note, or a minor loss in power could signal the start of blower or turbo trouble. But in the real world, these changes blended into the normal character of the engine. Operators accepted these traits as just part of the deal. That meant failures often felt like they came out of nowhere. Crews didn't ignore the signs out of carelessness. They simply didn't know which of the familiar noises or shakes was the warning they should have heeded. By the time the real trouble started, it was usually too late. The design of the air system itself contributed to the risk. The blower was gear-driven off the engine, which meant when a failure occurred, it could do damage beyond just stopping airflow. A stripped gear could send fragments into the timing gear train. A seized rotor could crack the blower housing or damage the drive shaft. Turbo failures could lead to pieces breaking free and entering the intake path. When these things happened, they didn't just stop the engine. They sometimes left it needing major repairs before it could ever be restarted. What made the truth scary wasn't that the 12 V71 had a weakness. Every engine does. The scary part was that the engine's reputation for durability and simplicity hid that weakness so well. Crews trusted the engine because it had earned that trust through years of hard work. But that trust made it easier to overlook how much depended on a single system that had no backup. By the late 1970s and into the 1980s, the Detroit Diesel 12 V71's time at the top was running out. It hadn't failed because of poor design or lack of capability. Instead, the world around it changed in ways the engine couldn't keep up with. Emission standards were tightening fast. The two-stroke diesel design, with its high fuel consumption and smoky exhaust, couldn't meet the new rules without fundamental changes. The 12 V71 had always burned fuel at a rate operators accepted because of the power it delivered. But now, with stricter regulations and rising fuel costs, that appetite for diesel became harder to justify. At the same time, operators were looking for engines that could do more with less. The industry needed power plants that ran cleaner and made less noise. The 12 V71, with its characteristic leaks, vibration, and roar, started to feel like a relic. What had once been seen as normal wear and tear now stood out as inefficiency.
Don't even have it running on any fuel. It's just what was in it.
Detroit Diesel saw this shift coming. The company introduced the Series 60 in the late 1980s, a four-stroke inline-six diesel designed from the ground up to meet the new demands. The Series 60 brought electronic controls, better fuel injection, and improved emissions performance. It was quieter, cleaner, and far more fuel efficient. The market responded, and the Series 60 quickly became a dominant force in trucking and other heavy applications. Other manufacturers followed the same path. The days of big, naturally aspirated or simple blower-fed two-stroke diesels were over. Engines with electronic management, turbocharging, and advanced fuel systems became the standard. Regulations and economics didn't leave room for engines that couldn't adapt. Despite all this, the 12V71 didn't vanish overnight. In marine work, off-road equipment, and backup generators, the engine kept finding jobs where its simplicity and raw strength still made sense. Some tugboats and supply vessels ran them well into the 2000s. Logging outfits, especially in remote regions, kept them alive because they could fix them without computers or specialized tools. Enthusiasts and collectors also kept the legend alive. The unique sound of a 12V71, that high, urgent chatter of a two-stroke diesel underload, became part of its identity. For many, hearing one still brings back memories of trucks, boats, or equipment that got the job done when nothing else would. In the end, the 12V71 story was one of strength overshadowed by a flaw. Its simplicity and mechanical toughness hit a critical weakness in the air system, one that cost crews dearly when it failed. Rising fuel costs and tightening emissions rules played their part too. But that hidden vulnerability did as much as anything else to mark the end of its era.